this quarantine. I remembered my chisel to open his rock, and he didn't show up this morning. Unless he did it when I was running back and forth to Ava. Let me unfreeze this. I got my remote working again. Just had to smack it around a little bit. And it dropped so many times. All right, we started plate tectonics or continental drift. It means the same thing. Yesterday, we're going to talk about the major types of motions between either a continental plate or an oceanic plate. We did talk about, I need to get this finished off the board, this opener, but we were looking at a map of the world, the one that had all the rifts that looked like the seams of a baseball on it. It went directly, like straight down, well, not straight, but it went from Greenland down to Antarctica in between the Western Hemisphere and the Eastern Hemisphere. Where did South America fit into on the other side of the rift? Where does it fit? What is it, like a puzzle piece? Where does South Africa go? Or where did it come from is the better way to phrase this. Because I didn't implant a lot of these images into your canvas. It would have, your notes page would have been like 4 pages long if I would have put all these pictures in there.
Africa.
It fits perfectly in Africa because that's where it came from. And I'm going to come back and I'm going to show you some images of the rifts again. It's not quite as large as that one that we looked at yesterday. But that was one of the reasons why Wegener said, I think all these came from one big supercontinent, which he called Pangea. He did base it off of the way that they physically look. He based it off of the way that the rocks are layered. He based it off the fact that index houses match on opposite sides of the planet. We didn't have modern technology, which is why his science cohorts thought he was nuts. Now, we've proven that he's right. It really shouldn't be called the theory. Oh, that's not animated right. Let's fix this. I forgot to do it by, hope this is the only one, because I just did it this morning. By paragraph. If I don't tell it by paragraph, that's why it all, at least I figured, stop, present. All right, it should be working now. Come on, no. I gotta get rid of them all. Hold on just a second. You guys get to see how I have to do this. By paragraph, add animation. Present. Now it should work. Now it works. Let's see how many of those I have to fix. I didn't change this around until this morning when I got here, and we were running a little bit late this morning. Okay, but we are starting up plate tectonics or continental drift. They mean the same thing. And plates, you will. You need to learn some of this. That doesn't surprise me because there are some things that do spread out into other classes. They do. But the crust in the upper mantle, okay, that's the asthenosphere, those make up what is called the lithosphere. We talked about this yesterday. It breaks apart into plates. I have to count them all up. Australia, or possibly the area of the ocean that's off of a certain part, like Nazca, which is off of Peru. They're named after where they're located. Obviously, we're on the North American plate. South America is on the South American plate. Most of them make complete and total sense. But the plates move on top of the mantle because the asthenosphere is on top of the mantle. It's the upper mantle, which is a little bit more thick, I guess would be the right phrase. It still can flow, it just does so slowly. It's not as molten as the middle mantle, which has all the convection currents. But they literally float, plates float across the top of the mantle because they are less dense. If they were not less dense, they would sink and we wouldn't have any continents. We would not have an ocean floor. Lots of cross sections. So yesterday we said the crust is on the outside, the crust in the asthenosphere, which is sort of this grayish section underneath it, that's the lithosphere. This yellow part is the mantle, the orange part is the outer core, and the inner part is the inner core.
You put this for theory of plate tectonics?
Let me look and see what I put on my papers. No. That should be on this one. There we go, theory of plate tectonics. Really, it shouldn't be called a theory anymore. Well, we watch it move. The plates move slowly, anywhere between 1 and 20 centimeters a year. It's when the pressure builds up, like the ones that move side by side, that we get the noticeable earthquake kind of stuff that happens, like in San Andreas. And no, California is not going to fall off into the sea. San Francisco will flood if it breaks through out into the ocean. But both types of crust, both oceanic and continental, are moved by the asthenosphere. Where the plates come together, it goes deep down. That's where the big cracks are, that goes deep down. And it allows that magma to come up, and then as it leaves the ocean floor, even though it's under the water, that's technically lava, which cools very, very, very quickly. It is driven by convection currents that are in the middle mantle, not the upper mantle. The upper mantle is the asthenosphere. It's technically part of the lithosphere. And they're moving in different directions, depending on where they're located. I will show you an image, which, like I said, I did not implant any of these into the, I guess I could have, because it's only on one side. I didn't put them in there. But I do have a map that shows you with arrows the directions that the plates are going. And depending on if it is a oceanic crust or a continental crust, there's 3 different combinations that can occur in between them. Either you're having a continental and a continental coming together, you got an oceanic and an oceanic coming together, or you have a continental and an oceanic coming together, and they all have specific features that are associated with them. This is sort of what we were looking at. They just don't look like the baseball scenes that has the little hash marks going down it. This is the Mid-Atlantic Ridge. This is the one that broke Pangea literally in half. And it extends all the way from Greenland down to this Atlantic Ridge, which is this one on the bottom. When you have a ridge in the ocean, where that lava comes up through the crack, it pushes the material out in opposite directions from the ridge. And the answer to the opener was yes, South America fit here. It fits almost perfectly there. North America fits over here, but this part fits over here. That Mid-Atlantic Ridge is the longest chain of mountains on the entire planet. Most of it's just from the water, so you can't see it. This is an image a little bit more scientific than some of the other cross sections that I've shown you. These convection currents, you have being heated from the outer core, your molten earth, which is primarily all the compounds that make up granite, silica, oxygen, aluminum, those. As they heat, they rise. Then they go towards the surface, they start to cool off, they become more dense, and then they sink. And if you notice, they're doing it in opposite directions right underneath one of these. In this case, it is the mid-oceanic or mid-Atlantic ridge. So your asthenosphere with this circle on the right-hand side of the rift is pushing it to the right away from the rift. The convection current on the left of the rift is pushing to the left. That is why these things are pushed in opposite directions. This is particularly oceanic ridges. Like I said, you're more than welcome to, if you want to, Google these and stick them in with your notes. But that's what's happening underneath the earth. Does it actually show a circle? No, but that's the way that they're flowing. So that asthenosphere, the part that's directly underneath it, is this is technically, this is it that's pushing it. And we've got continental over here. We've got oceanic, which technically is gray. The asthenosphere is right underneath it. But your oceanic is more dense because of its materials that make up the basalt, and then they're going to sink underneath the continental and push them up. Plate boundaries do go deep into the lithosphere. That is how the magma starts to come up. And like I said, once it leaves the ocean floor, it's technically lava. It's just underneath water. It's not on the surface. Then they make what are called faults. There's different types of boundaries. There's different types of faults. We're not going to get into the same depth with them because we have a 45-minute period, and this is the last one for your this section is the last one for your book check, which I'll share my screen and I'll show everybody where you can access this stuff. After today, if you really want to be that person that just has your stuff done, I would organize your notebook, get them in the right spot. I don't have the turn in activated yet. If you need a refresher course on how to do digital submissions, I have some students that are new to campus from other schools. They've never used Canvas before. That's what we're doing Monday. Tuesday, we will review for the 6 weeks test. I have not built your 6 weeks test. I have not built a review for it. I have not built a review for it. It will still be accessible online. Okay? As long as I remember to publish it, because those of you, if you were trying to retest, I made the retest, I invited everybody, and I forgot to push the little publish button, so I did that this morning. I sent out an email apologizing to those of you that wanted to retest it.
Also, is this your test from the newer test?
It's still in the newer test that we just took, yes.
You already put in the algorithms.
I did. It should be in Parent Portal and on Canvas. It took me, yours I didn't get graded until about second period, just because I had to hand grade it. The computer couldn't do it for me. This is an image of the bulk of the plates. Now, the plate boundaries have two different things that you can call them. I put them both on the next slide. But where they are, let's see, here is the Mid-Atlantic Ridge. It is red. This is the one that is divergent, is pushing things apart. The yellow one is the one where they're slipping past each other. This is actually the San Andreas Fault right here. And then where it's blue, they're coming together. So there are three major types, and there's two different ways to phrase them. Divergent or extensional, it's extending out from the center. It is moving to meaning two, like carbon dioxide from chemistry, two different directions. If they are convergent, they are coming together, they are compressing. This is how mountains are formed. And if you have transformed, then they're slipping past each other. They're not going on top of each other. They're transform are not going underneath each other. They're literally building up pressure until it slips. And that's the type of fault specifically that the San Andreas Fault is in California. We're going to do each one individually. You may want to add next to divergent boundary that it's also called extensional, that convergent is also called compressional, and transform is also called sliding. The words over here on the right are actually the less scientific terms. But since I have not built your test yet, and I use the questions from that generator, I don't know how I'm going to word it. I'm going to do divergent first. Two plates move away from each other, from a rift, specifically if it's subocean. They are going in opposite directions, away from each other, not towards each other. C4 spreading, which we talked about yesterday, is caused by a rift. Okay, that was when I showed you the convection current. Solid cut, how they were going in opposite directions and it was actually coming up through the crust in the center. That is a rift. So you got, whether it be oceanic, okay, or it be continental, the plates are trying to move away from each other wherever the lava is essentially coming up, whether it's on the surface of the earth where we can see it, or it's on the surface of the earth underneath the ocean. It's still outside of the earth, it's still lava. Once again, the largest mountain range on the entire planet is the Mid-Atlantic Ridge. From the top to the bottom, well, down to the Atlantic Ridge, or not Atlantic, the Arctic Ridge. No, I said that wrong again. Arctic is north and Antarctic is south, so the Antarctic Ridge. Oh, I forgot to animate this the right way. Now I'll fix it. We'll fix it. Figured I'd do another one, and I came across it, didn't even make proper. But it's okay. By paragraph. No, I have to redo the whole slide. I don't know why it does this way sometimes and not others. Still doing it. This slide may be stuck this way. Add animation by paragraph. Add animation. No, it's stuck this way. So when your rock is pulled apart, it's going, if you have like, in the examples I give you are like chewing gum, which is disgusting if you pull your gum out and play with it, but all kids do it. How when you pull it different directions, eventually it gets skinny and then it breaks in the middle. That's tension. That is what this is. It's just not doing it with gum, it's doing it with a rock. Once you have the breaking, we have what's called a normal fault. Now, normal faults are different than reverse faults. In a normal fault, when that rock is broken apart, the piece that breaks off from the main chunk is going to fall down some. The reverse fault is coming together and it's one of them's pushed up. But a normal fault, which happens at divergent boundaries, if you have a piece that breaks off, it's going to fall down from the original rock that it's breaking off of. The faults are related to earthquakes, and we'll get into all of that after the break. So other phrases for divergent, if it helps you, it's dissecting it. It's pulling it apart. It's breaking it apart. It's dividing it. And that's the example I gave you. If you pull apart gum, which is nasty, please don't do that. If you pull apart gum, it's eventually going to break in the center. This happens specifically both on land, which is continental, and this happens in the ocean. Underwater. You do not remember H2O is water. You should. Once again, divergent. It's extending away from the rift. We're going in opposite directions away from the rift. This is what the mid-Atlantic ridge specifically is. It's the entire part of it is a divergent boundary. The mid-Atlantic ridge is the primary reason why Pangea split. Specific features of divergent boundaries. The mid-ocean ridges, we're going to be talking about the mid-Atlantic more than anything else because it's the largest one. They make rift valleys, and they make fissure volcanoes. Iceland is a really good example of this. This is a map of Iceland, and it has a divergent rift going straight underneath it. And all these little triangles, those are volcanoes. Iceland's primary energy source is geothermal. They use it to heat their homes. They literally collect steam from naturally occurring vents and they pipe it through the house. This is a topographical map of Iceland. And you can see smack dab through the middle of it is this volcanic chain. It's because underneath it, there is a rift. I don't know all the names of their volcanoes. Iceland has weird names for their stuff. Lots of J's, fjords, and Greenland's like that too. The convergent boundaries. These are ones where two plates are coming together and they are going to collide. They are going to slam into each other. They compress where they meet. Now, depending on the type of plates that are doing this, different things are going to occur. They are going to strike each other. Sometimes one goes underneath another, sometimes they just build up in the middle. My computer just died. Hold on. Hold on here. I apologize. I gotta get everything back up. I present the tab to this one. It better charge. Okay, where were we at? We were right here or here? Here. This one. The second one? This one? This is the one I think we were working on. Okay. Hopefully my computer doesn't die again. I don't know. I must not have had it. I don't know. All right, so so when two plates come together, different things can occur. There's three types. We'll talk about each type in turn. But you're going to have, in two of the types of collision, things will be going up. And in another type of collision, you're going to have what's called a trench, but then you're going to have an uplifting on the other side, which is how Japan was created. I hope there's not something wrong with my charger charging. That would be horrible. Let's see. It says it's charging. It's at 8%. Yeah. Okay. Well, it happens. You just gotta roll with it. All right. Convergent boundaries. I really hope it's still recording online too. Let me freeze this and double check them. It says it's still recording. Once again, I do apologize. Oh, let me check their attendance. I do apologize, my computer died. DC Decker. And there's Kaden. There's Natalie. I guess that's what happens when you're completely and totally dependent on technology. I'm just waiting if we all go remote when, like, Wi-Fi goes down. Like, if my Spectrum goes out, I guess I just wait. But if that does happen, what I am planning on doing is in first period recording as I go through this and posting that immediately so that I can let other classes watch that while I help my child. All right, so a lot of times you have what's called subduction, which means one plate goes under another plate. This happens when we have specifically oceanic and continental occurring. So this is, the Nazca Plate is off of Peru, and it's pushing down underneath the west coast of South America, which has built that giant mountain chain that's in, what's on the left? Is it Chile? I think it's Chile on the left. I might be Argentina. I don't know. My geography is not like great. But these are just different examples of one going underneath another. Now, continental can be continental, and that's going to push up your largest mountain ranges, like the Himalayas. So 3 types. Type 1 is when you have an oceanic plate colliding with a continental plate. The oceanic plate is going to go underneath the continental plate because it is more dense, and it's going to push the continental plate up even more. Once again, the oceanic is more dense because it has the heavier elements in it, which comprises basalt. The continental has the less heavy elements, which primarily compromises granite. I don't know if I put a picture on here. I don't think I did. Oh, but there is one more. What likes to happen here at a subduction zone is a volcano. There are very, very specific surface features that appear in each of the types of convergent boundaries. I said divergent likes to make a rift valley. And they spread apart. It is literally like when you get a nice nasty cut or stripe and it starts to scab, and then you move the wrong way and you start bleeding again because you pop the scab off. Well, I mean, it's what happens, but it's not a scab, it's lava from the earth. Eventually that thing cracks and then upwells more stuff. This is a nice big image of what is going on. You have your more dense oceanic that is being pushed down underneath continental. And like I said, a lot of times you do have volcanoes. Mount St. Helens is the one that's up in Washington. I don't know all the names of my volcanoes. Type 2, oceanic plate. Hitting an oceanic plate. These make trenches. This is how the Mariana Trench was created off the coast of Japan, which is the lowest part that we have found in the ocean. I don't know if we've actually sent people down. I know
Yeah,
well,
because there was a video of it, of him actually going down into the
all the way to the bottom though.
Yes.
I'll have to double check that because I didn't think that we could struck anything that was strong enough to be able to have a pocket of air for us to breathe in. Because
he was struggling. They had lost connection from the boat to him, and they finally got him to do it. He finally got back up.
I'll have to look into that because that has to be something. You said it was last year?
Yeah, well, it wasn't last year. It was last year that I watched the video.
Okay. Because I have an older IMAX that takes down a bunch of submersibles and people not quite as deep as the submersibles, like the robot ones, and they take all this footage of the life at the bottom of the ocean. It's perfect class time-wise. It's just from 2005, and a lot of it is outdated. The space exploration stuff they start talking about is scrapped and replaced with other technology. I'll see. Over the break, I'm going to see if I can't find some things that we can watch to go along with it. It's not just all notes and manifest, and we'll have things that we can do in between. Because I have 2 weeks to actually have time to research stuff, and it's not 18 hours of doing Earth space on Saturday and Sunday and not having time to do anything. Type 3, a continental plate hitting another continental plate. This is where we have mountains going up. You're still going to have one go underneath the other, but the one that's going underneath is going to push up. This is how the Rockies were formed. This is how the Himalayas were formed. So ocean likes to make a trench. Ocean continental likes to make volcanoes. Continental likes to make mountains. There's not, I mean, they're long, but there's not that much because there's so many pictures. So mountain ranges. So that's how you spell Himalaya. And the Rockies are in the United States. That's on towards the west coast. That's the larger, that is the younger mountain chain. The eastern one, the Appalachians, are the older mountain chain. They're not as tall. This is an image of the Rockies. If I am not mistaken, that is from Teton Park, because that sure as heck looks familiar to me. I have been there. I've driven right through it. This is the Himalayas. They're your largest. Mount Everest is the tallest mountain on the surface of the earth. They are a much larger chain. All right. When you have squeezing with compression, not touching, which was tension, squeezing with compression, you have the other major type of fault. The tension made a normal fault, where if not this type, the first type we talked about, where if it breaks off, that chunk that breaks off falls. In this case, reverse fault, when they're squeezed together, one of them gets pushed on top of the other. It is a reverse fault. I'm almost there, and then I need to get after people who didn't make up that test that they were supposed to, not make it, but take the test from 2 days ago yesterday. Some people did and some did not. Because I think it's closed again. I need to double check it. Convergent. So as a review, convergent comes together. If it's continental, up. They crunch together, they go up. If it's oceanic and continental or oceanic and oceanic, it's going to go under and it's going to form a trench. So this is just sort of a recap of the other slides. That's why I didn't put it on your notes thing. It's just to reinforce. Transform boundaries. It's a different type of boundary. This is the one where they slip past each other. There are only specific areas where this occurs. And like I said, the most famous one in the United States is the San Andreas Fault. There are other faults in California that do this. That's just the big one. That's the one that causes the really big earthquakes. And they're probably overdue for another decent one. So they slip past each other. And what happens is these things build up pressure until finally one of the rocks gives and they jerk. And they move for a short distance quickly instead of much slower like they do down on the bottom of the ocean. If this stuff happens, these faults, if they happen underneath the ocean, specifically a normal fault, that's what triggers tsunamis. It's when a piece suddenly falls off and it creates a pressure wave. And as that wave comes closer to the ocean, the water has to go somewhere and it goes up. No rock is lost. It may be crushed into little bits in between them, but it doesn't disappear. It's pulverized. This is called shearing. Once again, they slip past each other. So a transform or a sliding boundary is the less technical term. Oh, we got like 2 more. It would have been done if my computer wouldn't have died. Let me check the battery, make sure it's charging. Yeah, it's charging. I don't know what happened. So at transform boundaries or sliding boundaries, once again, you build up enough pressure and the rock snaps. It jerks. And the larger distance it jerks to relieve the pressure in a shorter period of time, the bigger the number on the Richter scale.
There's 2 processes who made it continental around change. The first one was in 1916, he only made it continental around change. The second one was 50 years later, and he made it into the challenge.
Into Challenger's Deep.
All the
Okay.
way down to the bottom.
Okay, because it's like I said, the last time that I've seen any kind of, because I like documentaries, but the one that I have, it was produced in 2005, but the footage was also done, was obviously done before then for them to manufacture the documentary And- for the deepest. And the deeper you go in the ocean,
5,800.
it's insane. But we have an image of California here. And you can, this is the San Andreas Fault, where they are moving in opposite directions of each other. Now, if right here, this thing successfully cracks open and the ocean is allowed to flow inland, there goes San Francisco, San Jose, Santa Rosa. This whole thing fills and this becomes an inland sea. And it's going to do it very quickly. I'm not trying to give you anxiety, but if this fault has the big one that they keep talking about, the 10, there is a chance it's going to open a channel to the Pacific Ocean, and extremely quickly, that whole valley is going to flood. Like, you can't get out of the way kind of flood. It's probably not going to happen when you visit. Oh, you're moving to San Diego?
Yeah.
Oh, no. Well, we're all going to die eventually, but
I'll just be the one to die in horrible death.
I don't want that to happen. Now I got one more little slide. If it's a strike slip fault, with shearing, they will break. Okay, that's the part that pulverizes, and sometimes you have a decent crack, like what you think of as a fault. Where if you step into it, you're going to fall down into it. Let me freeze this and let me get and check my attendance one more time, double check the tests. I didn't double check my announcement to see if, I checked it when I was supposed to activate the test yesterday, and I forgot to push the button until this morning, but I did check it yesterday. Anybody else that had requested, whoops, that's the wrong button, requested the retest, let me double check it one more time. That was one thing I ran out of time to check this morning. So, yeah, I don't see anybody else from yesterday. All right, now grades. Come on, computer, you can do it. All right, the one from yesterday, I'm going to do it from here because you may have entered your stuff since I last looked. But I'm looking for the opener and the assignment from Alex, the opener from Otis. This is the one from yesterday, which is open still. Both of them from Caitlin. The opener from Caden, both of them from Esai. The opener from Taylor. Both from Erica, which I know you weren't in here. Both from Courtney. The assignment from Kale. Both from Decker and both from Colton. This is yesterday's assignment. Now the test from 9th. Let's see. I don't think any of the people that did not take it like they were supposed to are online right now. Let me double check who's online. Now, let's see. I gotta love doing 4 things at once. It was Alex, who's not in here. It was Otis, who I don't see online. Mauricio? No, who I don't see online, but everybody else took it. There were 3 people in here that requested the retest. I'm sorry. I sent out the info that it was open. I made it, put you all on there, put the start date and the stop date, and I forgot to push the little publish circle. So I did do that this morning, and I sent out an email apologizing that I forgot to publish it. But if you were wanting to retest, you would have gotten that email. Okay, so I'm going to stop this. I'm going to share the way I'm presenting real quick if I can get my computer to behave. In Canvas, and we will be doing this Monday, decided that it would just be best to give everybody a day for organization for your notebooks since it's a test grade. the module for next week, you take it on your view. Okay, so this is what y'all will see. And here is your notes list, which I'm gonna have to make a copy because I also re-uploaded. Now this is from the first 6 weeks, but how to do digital submissions, just replace first 6 weeks with third 6 weeks. Y'all, there was a bunch of them. It's not frozen, shoot. It is frozen. No, you tell me it was frozen. Back to it. Okay, so if you go back into Canvas, if I go back to what you guys see, this is next week's module that I've already started building, and you would click on this third 6 weeks notes list. Here's the YouTube link. I'm sorry, I didn't remake one because the one from the first 6 weeks looks great. This is what you're gonna click. Y'all, there are 20 things. 20 things, so that means each one is worth 5 points. So in your drive, if I figure out where my stupid drive button is, I would drag everything into your Earthspace folder. Get rid of that. Delete. Where's my trash can? Ugh, I don't see it. I would drag everything into, like this belongs in the Earthspace. I would create, if you have not done it, your third 6 weeks, I would drag everything into there. And then I separately put my notes into their own. The one that was the tie over from last 6 weeks was this one. This was the last thing we did before the 6 weeks exam. This one belongs in this 6 weeks, not last 6 weeks. So if you can't find this, check in your second 6 weeks one and make sure that that's not where you ended up putting it. But there are quite a few. There are 20 of them. And once again, that's what we plan on doing on Monday.